code. Okay, it's my big pleasure to introduce Ilia Zharkov from Manhattan in Kansas. And Ilya will speak about topological SYZ fibrations with discriminant codimension 2 based on joint work with Helge Rudat.
All right, thank you very much for the invitation to England, or whatever, Scotland. So I'll do the slides because there are several pictures I want to share. And so let me start with history, a little bit of history of the subject. And so this Strominger-Yale-Zaslow conjecture came out at around 96, I believe, and it says roughly, it's a physicist's conjecture, so it's very imprecise, but it says roughly that if you have a Calabi-Yau manifold, then that manifold should fiber over the half-dimensional base. Like if it's n-dimensional complex manifold, then the base should be n-dimensional real manifold. And the fibers should be Lagrangian, special Lagrangian tori. So everybody understand what the Lagrangian is. So but the special is the condition that they're calibrated by the imaginary part of the holomorphic volume form. And this is a difficult question. Analytically, you have to solve some very non-linear differential equations, and so the question is actually very, very hard. But the idea is very nice. So in a sense that that's the way to understand mirror symmetry, because the mirror would be then essentially, if you just take the dual torus vibration, that's supposed to give you a mirror. All right, that is very nice if the base is smooth and everything. So that gives you, two integrable system. One is a dual of the other. The problem, of course, is that you're not going to get any interesting Calabi-Yau manifold this way, because if you have all the fibers are tori, then the Euler characteristic is 0, so it's not very interesting. So no compact Calabi-Yau manifold except abelian varieties would have such thing. So the question is always what to do with the singular fibers. What are they, and what can we know about them? Can we somehow describe them or make any statements about those singular fibers? And this is again very, very hard question. So it's probably the conjecture is not correct. So it's probably false. At least nobody knows how to address this conjecture, but the singularities are, morally speaking, because you have two dual things, so the singular fibers have to be in codimension 2 on a base to have this compatible with the dual fibration. And there was some work of Joyce which kind of argued that, okay, special Lagrangians, it's unlikely to have if there are special Lagrangian torus fibrations, then unlikely to have the singularities in codimension 2. So people, I guess after like several years of trying, people more or less abandoned this special Lagrangian question. And then several years later came Kontsevich-Soibinman. They somehow said, all right, so this is probably conjecture as it stated originally, kind of hard to believe, or even if it's true, but it's impossible to prove. So they've made a little weakening of the conjecture. First of all, they forget the special Lagrangian property, and then say that it's only true in some limit. And so more precisely, so they formulated another conjecture, which is also still very hard, which says roughly the following. So suppose we have a family of Calabi-Yau, which has a maximal degeneration, namely that the monodromy around the degenerate fiber is maximally unipotent. And then we can fix a Kähler. I mean, all these members of the family, they are all homeomorphic, and so we can kind of fix a Keller class for all of them, and then take, or at least maybe take array or something, like the real array in this family, and then fix a Keller class, and then pick a Calabi-Yau metric in this class. There is, by a Yau theorem, there is a unique Ricci-Fleck metric in each Keller class. And now look at this thing kind of from a metric perspective. So you have your Calabi-Yau, you have a metric on it, and then you wanna, as you take this limit towards the degenerating fiber, then you want to follow what's going on with this as a metric space. So in some sense, and of course you want to some control so it doesn't get very, very large. So you want to scale your metric so that this whole thing stays over fixed diameter, for instance. And then there is a metric limit. This Gromov-Hausdorff limit always exists. This is like a general fact of about the metric spaces. And the question is, what is it? And so they've conjectured the following description of the limit. First of all, this B, this limiting space, is half-dimensional. If again, so if X was the n-dimensional complex n-dimensional, that the limit would be a real n-dimensional manifold. Well, I guess there is a debate whether it's a sphere. I don't think they've conjectured a sphere, but in all the examples, it is a sphere. And this sphere has a integral affine structure. Well, of course, the sphere cannot have integral affine structure, so we have to exclude some discriminant where the affine structure does not exist. So, and that thing has to be, this discriminant D has to be of codimension 2. And now once you exclude it, that on a remaining part, so-called the smooth part B0, there is an integral affine structure, which essentially means that the tangent bundle has the a flat connection whose holonomy is SLN Z. All right, that's the first part of the conjecture. And then the space B, since it's a metric space, so it's a metric, and this metric is a so-called Monge-Ampere metric. So first of all, it's potential, namely that locally it's given by the Hessian of some convex function, and Monge-Ampere condition says that determinant is equal to 1. Again, this is I think very, very hard conjecture in general. And I'll explain maybe later on what's the problem is dealing with this metric things. I guess maybe I'll say we don't know much about the Calabi-Yau metric itself. So there is like no explicit construction or anything of a Calabi-Yau metric. So if you try to prove this conjecture, it's not clear, how we're gonna, explain what's the metric limit of the Calabi-Yau metric, because we don't know it. And even for the local models, we don't know what's the Calabi-Yau metric is. So metrically, this is a very difficult conjecture, but well, we can start asking, what can we say, like from a very, very basic level, like topologically. So this is what I'm going to address. So I'm going to address just the topological part of it. Okay, and maybe one word. So since there is a well-defined integral sections of the both tangent and cotangent bundles, so we can easily form a torus fibration over the smooth part. Just take the tangent bundle and mod out by the flat sections which are integral. So locally, this is just a real vector space at each point, modulo some lattice. So this is a torus, and this torus varies as we move around the B0. Of course, it has some monodromy and stuff like that given by the monodromy of the connection. So that's the proposed mirror pair. And the question, of course, again, how do we continue this into the discriminant locus? All right, that's about all I want to say about. Oh yeah, a little bit more of history. Then Gross and Zibert program started maybe again early 2000. So they asked the opposite question. So you start with the integral affine manifold. What can you say about the potential family of your Calabi-Yaos? So in another sense, if you start with the integral affine manifold, can you reconstruct your two mirror Calabi-Yao? So this is the question I'm trying to address in this talk. Maybe it's rather a motivation for introducing a couple of new tropical objects. That's at least for me. So, all right, so I'm going to follow Gross and Zibert input data. What do we assume about the base and the discriminant and the monodromy, and then try to convince you that you can actually at least construct a topological space, X and X check, which fibers by general fiber being a tori, and with a given monodromy and everything. And also, I'll try to argue that you can actually compactify it over the discriminant locus into, in general, it's going to be an orbifold, but in good case, it's going to be a topological manifold. Okay, that's my historical part. Let me now start mathematics. Okay, so we start with a base B, which is a manifold. I'm going to work in PL topology, in PL category. Whenever I say manifold, I mean PL, the top PL, and all the homeomorphisms I'm going to claim they're going to be in PL category. So we want a manifold first, which is given a regular CW complex structure, namely that we break it into cells, and each cell looks like a ball, and the closure of each cell is a closed ball and stuff like that. So that allows us to talk about the barycentric subdivision. So just pick any point in the interior of every cell, and then you have your barycentric subdivision, which is a simplicial structure now. And so the discriminant has to be in that barycentric subdivision. It has to avoid all the neighborhood of the vertices, and it cannot be also in the interior of the facets of the maximal dimensional things. So we remove all the facets, and we remove all the neighborhoods of the vertices. So what we are left with is something of codimension 2 subcomplex. And the discriminant is not necessarily this entire thing, but it's a subcomplex in this codimension 2 subcomplex in the barycentric subdivision of B. All right, and now comes the monodromy assumptions. What do we assume about the monodromy? So I'm going to list them in the next page, but the starting thing, so pick any stratum in a discriminant, which is a strata in a first barycentric subdivision. Pick a point which is actually a smooth point, like just move it a little bit off the discriminant, and then you're trying to look at all the loops around the discriminant and say something about what's the condition on the monodromy. So first of all, there are two invariant sublattices. One is the invariant in a tangent space, and the other is the invariant, the co-invariant sublattice. So these two have to have the following structure in it. So there are R, which may be R equals 1, convex polytopes. The first series, they live in an invariant lattice, and they're kind of transversal one to each other. So the lattice each one of them spans, they sit linearly independently in this invariant lattices. So for every pair delta one, for every delta we have a delta check, and those are the polytopes which sit in a co-invariant in a co-invariant lattices, and those delta and delta check they kind of orthogonal to each other. So if you just take the span of all of them, and the span of all deltas is orthogonal to the span of all delta checks. I'll give an example in the next page. So, and these polytopes have to be somehow compatible as we move from a strata to strata. So if you have a smaller strata in a discriminant, say tau, that means that there are more loops around this tau. So in particular, we have always an inclusion of the invariant lattice in a bigger strata into the invariant lattice of the smaller strata, because the smaller strata, as I said, so it has more monodromies, because there are also other strata which attach to it. So, and under those two inclusions, the corresponding polytopes have to be, the face of the smaller polytopes have to be, the smaller polytopes means that the stratum is bigger, have to be the faces of the polytopes over this low dimensional strata. Okay, and so this is the first condition. And the second condition, that what's the discriminant itself looks like. The discriminant itself have to be in the following form. So if you take all those polytopes, let's just take one polytope. So let's take R equals 1. So you have a delta and you have delta check. If you take the normal cone to the delta, then what is going to be this, standard fan for the, well, at least when delta is like a simplex, for instance, which I'm going to assume next. This is just a standard fan for the projective space, and then you remove the maximal stratum from there. So what you are left with is so-called the tropical hyperplane. So and then you do the same thing for delta check, and then if they don't the entire space, then you have to complement these two fans. Take the product of them, and then you have to complement it by this RS. So the invariant and co-invariant stratum may be together. They don't have to be complementary dimensions. So in some sense, there is a factor which is just a stupid factor of R, which is in some sense both co-invariant and invariant. And then the monodromy. Okay, so in these two normal fans, what are the maximal facets? The facets are given by they're dual to the edges of the polytopes. So let's have we pick one of the facets. It's a product, so it's a product of the facet which is dual to the edge E in delta and the edge F in delta check. And then the monodromy, okay, so each edge, it's not just an edge, it's actually a vector. So if you pick a vector, there are two ways we can pick a vector for the edge, and that gives the co-orientation of the facets. And so the pair of the co-orientation actually defines you the way how you, which direction you go around this loop, around this facet. So if you do everything, correctly with all those co-orientations, then the monodromy should be given by this tensor. So it's identity plus just a single element in your matrix. It's given by the tensor product of those two, vector and the covector. So in some sense, this is the picture what's the monodromy looks like in a suitable basis. So you have a identity matrix, and then you have well, I'm not sure how I annotate. So you have this top right block here, where you have some, which is itself is broken into the diagonal blocks. Not diagonal, but it may not be square, but sort of this rectangular blocks. In particular, its local monodrome is always an abelian subgroup of this SLNZ, so it's given by this, top right thing, and in a suitable basis. So this precisely are the tensor product of the invariant and co-invariant lattices. Okay, that's the requirements, and then maybe I'll just give a couple of examples which are not what we want. So maybe before giving not what we want, let me start with what we want. So I didn't write it down, but if you replace all the 2's here by 1, so here there are -2, make it -1, and then it's 2, make it make it 2, 1, and then -2 is 1. Then this is a typical picture in dimension 3. So you have a discriminant, which is a graph here. So I've drawn 2 neighboring vertices of the graph and an edge between them. And so these 2 vertices actually are of different type. For one vertex, you have your delta. I think for the right vertex, you have your delta to be a triangle and a delta check to be an interval length 1. In the middle edge, you have both delta and delta checks are the standard intervals, and one interval becomes an edge of the triangle here. On the other vertex, the other interval becomes the edge of the delta check. And so this is how you transform between the delta check on one vertex and a delta check on other vertex by this middle interval here. Now the problem with 2 here, so everything is fine when you had to 1. So this is like a standard picture for the dimension 3. I think this is like the only picture if you want simplices to be unimodular. The problem with 2 is, so if you look at 2, suppose your monodromy around this middle edge tau is 2 here. Then this 2, you have to somehow, this is an edge of length 2 times an edge of length 1. And the way how you distribute this 2 between the delta and delta check, it actually differs. So this vertex here asks for the 2 to be in delta, and this vertex here asks for the 2 to be in delta check. And so somehow you're torn in between these 2 cases, and this is not good. So this is what we don't like. So we actually want the polytopes to be, compatible with the neighboring things. And maybe one more example of something which we do not want. So this is not a polytope, as you see. This is kind of, I mean, it's not convex. It's a polytope. Well, anyway, it's a non-convex twisted polytope, if you want to make it. So again, this is a picture in R3. You imagine, so this is a plane, and then there is one more direction. So the delta check is just an interval, and I'm trying to build the delta with those monodromies. So the monodromies are perfectly fine. I mean, they sum up to 0. I mean, the product is 0, so everything is fine. This is perfectly valid integral affine structure. In some sense, this is same as simple in a sense that if you look at it as a block matrix, then you actually see, very, very nice block matrix when you have 1, 1, 1, 1 on a diagonal, and a block would be just, this top, the right column, in this 2, -2, 1, 0, 0, 2, 0, 1. This is a abelian subgroup of SL3Z, so it's perfectly valid. But the problem is that it's not given by a convex polytope. So again, we don't want those, we don't to avoid. And moreover, we actually want all the polytopes to be simplices. So this is one of the consequences of the main theorem, which I'm going to I talk about. So we can actually, okay, so if we have all the polytopes to be simplices, then we can compactify it. And okay, so maybe again, so I'll give a little bit of history to that question. So moreover, we can give explicit what the singular fibers are in this case. If the simplices are unimodular, then well, for the X, we'll need the simplices deltas to be unimodular. For the X check, we need the delta checks to be unimodular. And then in this case, the compactified space is a manifold. So, all right, so there are two cases which I think this question was solved earlier. I mean, one case is sort of obvious when you have a two-dimensional thing with a focus-focus. So I guess everybody knows it. So if you have a elliptic, well, we have a T2 fibration over the base. This is, and the monodromy is kind of the shear, or maybe a multiple K here. Then there are, you know, if K is 1, there is essentially one way to compactify it by adding the fiber, which is a pinch torus there. And this is called focus-focus singularity, because this is probably known in like in 19th century for the integrable systems. If K, and or there are actually more than one way to do it, depending on how you split your K again. So in this case, both polytopes are intervals, so the product of the lengths is K. So the question is how you split your K into the delta, into lengths of delta and delta check. So it gives you a different compactification. For instance, if K is 2, you may have one way to add the singular fiber, which is twice pinch torus, or that's a manifold. Or you can add the fiber with a single pinch torus, but the monodromy is like it's twice. So this actually is in a total space. This is like a double point. So it's not a manifold. Moreover, in this case, Mark Gross and Wilson, they actually did the metric version of this. So they've started with S2 with 24 singular points like this. So, and they are the easiness of this case, because even metrically, we know what's the local structure of the Calabi-Yau metric is near those focus points. It's so-called Aguri-Waffa metric, so it's actually known, and it's very, very explicitly, it has a very, very explicit description. And the question now is, so you have all these local models, and now you try to patch them together. So Grosse and Wilson were able to carry out this patching, and the argument that's the total metric which you get this way is very, very close to being Ricci flat. So more or less, this two-dimensional case is kind of solved to the to the highest possible degree of happiness. And the topological version of this, Mark Gross again wrote a paper in 2000. I think he wrote it in 1999. About the quintic threefold. So for the quintic threefold, there were also known explicit models for the local compactification. Once you know the explicit model for the local pictures, then you can kind of glue them all together into a nice global manifold. Okay, and or maybe I'll go back a little bit on. So essentially, the input in this theorem are we just follow whatever the Gross did for the quintic threefold. Essentially, just trying to compactify, more and more fibers by following the Gross approach for the quintic threefold, and everything works fine. The question now, all right, so we get a space. All right, manifold. What does it have to do with the Calabi-Yau or anything? So this is we're trying to. So the next thing we're trying to compare it with the known spaces. For instance, if you follow the Gross-Zieber program, they require a little bit more than they require the space B with a polytopal structure on it, not just a regular CW decomposition, but actually the cells are the polytopes. And this extra phi thing, this is like the polarizations for the stars of the vertices. They want not just the fan structure with biaxial support, the convex PIO function supported on those fans. So in some sense, this phi is some kind of make sure that the dual affine structure would also be polytopal. And then they construct this space, which is in this log. This is actually essentially made out of, if you take all your polytopes, every polytope define a toric variety for you. So you take the union of those toric varieties, and then you can put a log structure on it. All this data gives you a way to put a log structure on it. Once you have a log structure, then you can form so-called Kata-Nakayama space with this log structure. All right, so this, I put a question mark here. I'm not sure about what's the status of the program is. Sometimes, I mean, Zibert and some of his collaborators, including the Rudert and Julia, what's her name? Julia. Anyway, so there are people working on this. I'm not sure, what's the final status is. So sometimes this actually comes from an analytic family, where this union of toric varieties is your central fiber. And then this Kata-Nakayama space is going to be homeomorphic to the general member of this family. But what we can prove in particular, that this Kata-Nakayama space is always homeomorphic to our space, which we compactify. So, which give us actually a description. In case this is a true degeneration, then it gives you topologically what's our general member of the family is. All right, here comes the problem. So in this Kata-Nakayama space, it has a natural map to the base, but the discriminant is not in codimension 2. So it actually does not map to the base per se. So it maps to some, so this discriminant has to be a little bit thickened into a codimension 1. So I'll give an example of this. So, okay, maybe this is like a general scheme how you build a local model. So there are two ingredients to that. So remember, you have this delta i's. So each delta I is defined defines a Laurent polynomial from C star to C by its vertices. So essentially, like take the polynomials whose exponents are the vertices of delta. So you have from the C star to the L. L is the total dimension of all these polytopes, the sum of the dimensions of the polytopes. You have the maps to the, you have R maps to C. On the other side, from the delta checks, you can build a toric variety. So just assume there is one of those delta checks. So you have your delta check, then you take to place it in one dimension higher, take the cone over it. So this is the usual construction for the toric variety. This is going to be just a single cone over the delta check. And this cone also has a map to the affine line given by you have a cone, and then you just project this cone onto the ray. And so this map is given, roughly speaking, by this monomial W in a dual cone, which evaluates 1 on all the vertices of delta. And you have more than one of those deltas, then you have a bunch of those W's. So anyway, so you have your toric variety. This is just a fine toric variety sigma. Then you take the moment map into its dual cone, and then you project down along all those W's. So this together gives you a map into your base, and the space, the local model itself, V, you form as a fiber product essentially with these maps from the affine toric variety to CR and the map from the C star to the L to the. there is this little subtlety about this finite abelian cover, because your simplices don't have to be unimodular. So sometimes you have to cover them by just, so this map down here is just a pair of pens. All these Fs are just the ordinary pair of pens. You lift all those pair of pens into this affine covering map. And also there is another ingredient in those affine abelian covers, that if you have a bunch of sublattices, they not necessarily, if you take the direct sum may have actually finite index into the sublattice over Q. So that finite abelian cover takes both cares of the this non-saturatedness of the direct sums of the lattices Li. Anyway, so I'll just give one example for this picture, which exhibits the problem also. So if you have your, this is so-called negative vertex in dimension 3 again. So if you have your standard 2 simplex, and delta is a standard 2 simplex, and delta check is just the interval of length 1. So then the local model, okay, so now your toric variety is just C squared, and your potential W is just XY. So, and the map from the C star, this F's from the previous picture, this is just a pair of pens. So it has a triangle, so the corresponding Laurent polynomial is just the vertices of this triangle, and then the fiber product becomes, okay, so this V is just when these two are equal, so that's given precisely by this equation into the product of the C squared and the C squared. And now let's look at let's try to analyze what's the torus fibration is once we use the moment map from the toric variety part and use the log map on this Newton polytope part. So, all right, so we map to R times R2, but now this is a T3 fibration, but let's see where the fibers are singular. The fibers are, okay, so this is actually going to be, all right, let me think about this way. So we can think of this as a S1 fibration over this R times this C star squared. And inside here, we have a surface, namely take the 0 here and our pair of pens in the C star squared. So this is where the feels to be a circle. This is where, so x equal to 0 and y equals to 0 and 1 plus w2 equals to 0. So you have just a single point. So you have this 5-dimensional space, R cross C star squared. Inside of it, you have a 2-dimensional surface. And you have a circle fibration over, this every point here, except the circles collapse over this 2-dimensional surface. So locally, it looks like a Hopf fibration. So if you have a R3 and you have an origin in it, then you can form, the circle bundle everywhere except the origin, and the origin collapse, and the Chern class of the circle bundle is 1. Okay, now the problem is that now if you look at the discriminant, this pair of pens maps not to what we want, not to this trivalent graph, but it maps to this amoeba thing, which is a flattening of the, a thickening of this graph. And so the idea I'm trying to propose here, how to deal with this, is actually to change this map. In other words, maybe another way to say it, so we're going to have another space here, not the surface, which is a pair of pens here, but another space which actually maps naturally to this trivalent graph. So anyway, before all that, it was just a motivation, roughly speaking. But now let me get to the point. So again, what we want is that we want a map from C star to the n to Rn, such that the image of the pair of pens here is the tropical hyperplane, not the amoeba, but rather the spine of the amoeba. All right. So, in other words, I'm gonna rephrase the question. So, what we really want, we want some other space in C star to the n, such that the pairs of that new space of the C star to the n, comma, that new space is homeomorphic to the pair C star to the n with the original pair of pairs. So I'm going to give you two candidates for that, and then you can choose which one you like better. I think I like both of them. So again, so the point is I'm going to replace my true complex pair of pens by these two objects, which one is an old object. I think the first time it probably appeared in Michalkin's paper on pair of pens decomposition, and also in Verro's papers on this hyperfield things. So this phase tropical, I'm going to explain what this is, but this phase tropical pair of pens and another object which I'm going to introduce, obertropical pair of pens. I don't know, I've named it obertropical. People may object, but that's I came up with this in Oberwolfach last year, so this is obertropical for Oberwolfach, if you want. Both are very, very interesting spaces. They are very, very non-trivial. But the point is, so the main theorem which I'm going to try to explain here is that all the spaces are isotopic. So in some sense, if you have your C star to the end, then you can isotope each of those spaces one to another. Okay, so I'm going to introduce the phase tropical first. All right, let me start with pair of pens. So pair of pens is just this linear, hypersurface in C star to the n minus, in C star to the n. In homogeneous coordinates, it's more convenient for me to use the homogeneous coordinates there. It's just given by this equation. The coefficients don't matter. We can always absorb them into the change of the coordinates. People also say, all right, so the pair of pens is, if you just take n plus 1 generic hyperplanes in projective n minus 1 space, then remove those, this is going to be the pair of pens. Again, you can always choose the coordinates such that these hyperplanes are the coordinate hyperplanes, and then it's precisely given by this equation. So it has two maps. I mean, the C star to the n has two maps. One is a log map to Rn. For us, it's going to be convenient to actually compactify to Rn into a simplex by taking not the log map, but the absolute values of the coordinates. And then the amoeba, it's the image of the log map. It just becomes the hypersimplex in this simplex delta. Why is it a hypersimplex? Well, because you can think of this equation being kind of, if you think of this bunch of complex vectors and whose sum is 0, that the only condition for those lengths to be such that the sum can be 0 is that this triangle inequality. So that means that if you normalize them to be the sum of the lengths to be 1, that means that nobody has to be a length of higher than 2. So the hypersimplex which we get is we take our simplex and cut off the corners halfway. And the Co-Amoeba, we also have the argument map, which is just take the arguments, and then we take the closure of this all the possible arguments. So I've tried to picture here two examples of the dimension 1 pair of pens, namely n equals 2 on the left. You have just the Co-Amoeba has just two triangles, and the picture on the right is example n equals 3, so it's a two-dimensional pair of pens. You have actually, I've drawn here only 3 of those octahedra, but there are actually 6 of them. And yeah. All right, so Y is now becomes the spine of the amoeba, namely the spine of this Hypersimplex in the simplex. So in this case, just this 3 rays here. The cones, of course, due to the faces of the simplex. The faces are essentially the subsets, and since we exclude the maximal cones from the normal fan, that we have to assume that J is at least 2 size of J. And for each such J, we also consider the partial co-amoebas, namely we take the sum of not all the coordinates here to be equal to 0, but only those which correspond to the corresponding subsets J. So, all right, and then we take the products of the cone corresponding to a subset J times the co-amoeba corresponding to subset J, and take all the union of all possible subsets J. So that's the picture I've tried to draw here in n equals 2 case. So you have 3 rays, and the biggest co-amoeba is over the vertex when we have all z's to be equal to 0. So there's going to be these 2 triangles, the red 2 triangles. In the square means this is a T2, and inside this T2 we take the fiber, which is these 2 triangles over the vertex. And over each ray, we take the partial co-amoeba. Namely, we have only Z1 plus Z2 equals to 0. For instance, over here, Z1 plus Z2 equals to 0. It means that they have opposite arguments. So it means we actually have the circle as a fiber of the argument. I mean, the possible arguments lives in this circle. And similarly, we have a circle which is Z0 plus Z1 equals to 0, and Z0 plus Z2 equals to 0 along this edge. So we have a circle here, we have a circle over this ray, and the 3 circles, they actually meet as a boundary of this 2 triangles over the central fiber. So anyway, I'll leave to your imagination what this thing looks like. It's actually not very hard, but it becomes, a lot harder in higher dimensions. So there was a conjecture of Viro that this is actually topological manifold. So we proved this with Kerr, and it wasn't obvious. But now I'm trying to claim the stronger result. Not only it's a manifold, but it is actually to the original pair of pens. All right, so for the obertropical, I'll need to introduce the skeleton of the co-amoeba. So the skeleton of the 2 triangles, I didn't draw it over there, but you can imagine that these 2 triangles, they have this skeleton which looks exactly like a spine of the amoeba. So essentially, the 3 intervals joining at the 2 vertices. So this is a picture of the skeleton for n equals 3. So we have a 2-dimensional pair of pens. The green thing is the zonotope. It's a complement of the co-amoeba. The complement of the co-amoeba is always the zonotope. So, and the skeleton of it is this permutahedron, which I tried to draw. Actually, Hege was drawing this picture. The point is that the vertices of the zonotope, they becomes precisely the centers of the facets of your permutahedron. So this is a picture on the right, kind of is in the universal covering of the T3. So you have this, the co-amoeba itself is between the gray zonotopes. So everything but the gray zonotopes is filled out by the co-amoeba, and the red kind of contour here is how the skeleton sits inside this co-amoeba. Anyway, the point I'm trying to make here is that the faces of the skeleton are labeled by the cyclically ordered partitions of the set from 0 to n. For instance, the facets here, let's look at the facets of this permutohedron. The facets are labeled by just the two partitions. So what are the two partitions? The facets, as you see, the facets of the permutohedron, they have exactly one vertex of the Co-Amoeba in it. So who is the vertex of the Co-Amoeba? The vertex of the Co-Amoeba correspond to like the real component of your pair of pens. So every vertex of the Co-Amoeba, the preimage of the vertex of the Co-Amoeba is precisely the real points, the points in one of the real components. And this two partitions says, all right, which of those coordinates are going to be with pluses and which coordinates are going to be with minuses. And since it's up to reordering, like pluses can become minuses and minuses pluses at the same time, it's precisely this two partition. So the facets of the skeleton are the two partitions, and the the lower dimensional strata becomes labeled by the just more complicated cyclic partitions. So cyclic partitions means that I break my set 0 to n into the subsets, which are, the subsets are ordered in a cyclic order. The elements within each subset are not ordered. And now I'm gonna tell you the order-tropical pair of pens is the following union. I take a cone in my tropical hyperplane and multiply it by all the facets, all the faces of my skeleton, such that this J is not in a single part of my partition. So I'm going to draw the picture for the two-dimensional case. The fact this is actually a manifold is not entirely not obvious, and it's kind of obvious in this case, though. But in general, the local structure is actually very complicated. So maybe I'll say a word if I have time. Anyway, so this is two dimensions. If you look at two dimensions, everything is so obvious, then you may think, all right, so everything is obvious. But even in two dimensions, I think it's not obvious that these two spaces are isotopic. I mean, they're clearly homeomorphic to each other, but can you make an isotopy between the two? It's actually, not so obvious. And you want the ambient isotopy, right? You want to map from C star to C star, which transform this pair of pens into that kind of thing. But let me maybe look at this maybe more explicitly. This is the order-tropical thing. So we have the two skeleta. One is the skeleta of the amoeba, called I called it Y before. I know why it's called S here. And then we have the skeleton of the Co-Amoeba. The skeleton of the Co-Amoeba, I've explained, consists of 3 intervals. So the green, this green is a half of this green, so it continues. This is a picture of the torus T2. And then we have this 3 components of the skeleton of the Co-Amoeba. And now each of them is kind of a half circle. For instance, if you look at this edge over here, then this edge in a spine of the amoeba would have a fiber which only has 2 of those half circles. So together they form this nice shape. But as I said, so in this case, it's sort of visually obvious this is a manifold. In general, it's not. Like in the next dimension, it becomes very, very difficult. And maybe I'll say a word here. The structure is the following. I mean, maybe I'll say it a little bit later when it comes. So maybe I'll have 5 minutes. So maybe I'll outline the essential idea. What what's involved in the proof of this isotopy. So the idea is the following. So first of all, we're going to break the torus into simplices by ordering the arguments. So this is how the T2 breaks into 2 triangles, and the T3 breaks into 6 simplices. They're not quite simplices because the vertices of the simplices is really just the same point. So those simplices, when the vertices gets identified. But since the Co-Amoeba and none of our spaces touches those vertices, so we don't care. We just separate them. So that breaking of the torus also breaks the Co-Amoeba into the chambers. So breaking this T2 into 2 things, so that gives us 2 triangles in a Co-Amoeba. So that's the picture which I was trying to draw, show you before. This breaking of the T3 into 6 simplices actually breaks the Co-Amoeba into 6 octahedra. And then, if you look at those decompositions, so we have this strata of the simplex of the amoeba part of the simplex, this delta, and then we have the simplices in a torus. So this is a product of 2 simplices, and then we take the corresponding, this P can be either the obertropical, it can be phase tropical, it can be the original pair of pens. So we restrict it to that particular chamber into the torus, and then the claim is that this is the standard ball pair. Standard ball pair means it's a homeomorphic to the k-dimensional ball, comma k-2 dimensional ball, like the standard one. And as you see, this is codimension too. So this is like the trickiest case, right? So we are in a knot theory. So to show it's a standard ball pair, it's actually not so obvious. Maybe I'll draw a picture in this 2-dimensional case. So this is the amoeba part. The blue part is the amoeba. The red part is the co-amoeba part, which is restricted to just one particular simplex. So in this case, they're both triangles. And the spine of the amoeba looks more or less the same as the skeleton of the co-amoeba part. This is not true in general, I mean, high dimension, because the actual skeleton of the co-amoeba is a little bit shifted. It's not, and the center is really not the body center of the simplex. But in this case, it is. And actually, interestingly, the co-amoeba itself looks exactly like the amoeba. So in some sense, there is this symmetry restored. If you just look at a part of the co-amoeba within this one chamber with a fixed ordering of the argument, then it's also a hypersimplex. If you think about it, so these are the set of arguments on a circle, and we just do not allow the arguments to lie on one half of the circle. So this is the same triangle inequality. If you use the alphas to be not the arguments, but the difference of the consecutive arguments. So this is complete symmetry restored. I'll call it like equal rights between co-amoeba and amoeba. So both spaces kind of looks very much the same. And then these are the 3 objects, 3 2-dimensional balls inside the product of this 4-dimensional ball, which is a product of the 2 simplices. One is the actual complex pair of pens. I'll try to draw it as a hexagon, although it sort of sits very, very non-linearly in the product of these 2 simplices. This is a phase tropical, so you have this fiber, which is a triangle over the vertex of the thing, and then you have this 2 rays times the, this edge of the triangle here. So we have this kind of, I don't know what it's called, but that's what's the ball for the phase tropical case. And eventually I've drawn the obertropical thing. So the obertropical thing sits entirely over the this blue skeleton times the red skeleton. And the way how you know which product of the two rays you take is sort of I've depicted it here. So this red ray, which is between A1 and between alpha 1 and alpha 0, gets producted with H12 and H02. So you have these two squares here. Anyway, I'll have to finish in a couple of minutes. But anyway, so I'm saying that in general, this is actually not an easy statement, because you have to show that this is a standard pair, and you are in codimension too. So this is the most interesting, of course, case, because we have the whole knot theory for this codimension 2 goals. And the essential argument is, maybe I'll just show that this is locally flat, and it's and the complement is homotopic to a circle. That's essentially there's two ingredients involved in all three cases, which you have to prove that this is a standard ball pair. Anyway, and eventually maybe I'll say, and now we can glue all these things together to get our wonderful SYZ vibration by replacing the original models with this tropical models. And maybe a couple of comments here. Once you do the obertropical thing, the fibers here over these circles, remember they're actually not the, they're actually not the straight circles as for the phase tropical one. They have this kind of wiggly circles. So once you start here, you have this trivalent thing over the vertex, and then once you move into the ray, this wiggle thing survives. And this wiggle thing, you have to kind of, unwiggle it as you move towards the boundary into the straight circle. In a phase tropical, as I said, so no unwiggling is needed, because it's true circles already, and so it's nice. It glues very, very nicely to the local models and the nearby. I'll finish in a minute. But on the other hand, if you try to look at what's the singular fiber is, then the obertropical has a clear advantage, because, for instance, in this case of the negative vertex, what's the singular fiber? The singular fiber in an obertropical case, you have this S1 fibration over T2, which collapses along this skeleton here. So it's dimension 3. I think it is actually immersed sphere, or something like that. I mean, it's a 3. It's still dimension 3. So we have, if you're trying to do, all this, symplectic story here, that you may think, okay, so that's maybe a good candidate for the actual Lagrangian fibration. In the obertropical case, the fiber is actually not equidimensional. If you look at the fiber in this negative case for the phase tropical case, then the fiber is still a circle bundle over the T2, but the circle collapses over the entire, these two triangles. So this actually is not even equidimensional. So it has some components which are two-dimensional here. So even the entire space is still a manifold, though, but the fiber itself is kind of ugly. Anyway, I'll stop here. Maybe it's a little bit over time. Thank you.
Thank you. Thank you, Ilya. Yeah. Any questions?
Ilya, can I ask? So your main statement is about primitive simplex, right? So do you know any more general statement?
Yeah, if my statement is only about the simplexes.
Okay.
But if it's not a primitive simplex, then I mean, everything goes very well with this finite abelian cover. This is completely, how to say, equivariant with this finite. I mean, all the constructions are, very, very, very you know, equivariant
even
with respect to this finite abelian cover.
Even ambient isotopy?
Yeah.
So you claim that everything is goes
equivariant.
through?
Yeah,
Right?
goes through for every simplex. It's not necessarily standard simplex.
Okay.
More questions? Okay. I cannot see any more questions. So if there are no more questions, let's thank Ilia again. Thank you very much. Do it in Zoom as well. Okay, Ilia, thank you very much. I recorded the talk and I will upload it to the seminar webpage in half an hour. Yeah.
I can send you the slides if you want to.
Yes, please. We'll do too.
Okay.
Thank you. Yeah, thank you very much. See you all next week.
Thank you for listening.
Bye.
Bye. Bye.